Laplace transformation is an excellent tool that helps us to solve equations by transforming its function and variable into a new function with a new variable within the same domain. And once that new function is obtained, the inverse transformation steps will help us to write the result in the form of our original function. This is a very important subject for all those who are interested in the field of advanced applied engineering mathematics and those research and design engineers that every now and then face in solving a challenging differential equation. I am going to show you step by step everything you need to know about this subject, starting with the definition of Laplace transformation and show you the common sense approach that Laplace did in order to come up with his transformation formula, and also show you the steps for the inverse transformation, and use some very basic examples and move into more challenging ones. And finally, I will show the application of Laplace transformation in solving some differential equations in actual engineering problems. I am sure if you follow my directions, you will get a very good result. So to start, let's assume that we have a problem that we want to solve, and we want to use Laplace transformation in order to solve our problem. Let's assume that the function of our problem is f of t. So the first step is we use the Laplace transformation formula and we transform our function and variable into a new function with a new variable. Laplace transformation of f of t by definition is Laplace, this is the sign for Laplace transformation of f of t is equal to the integration from 0 to infinity of e to power minus s of t f of t dt. Now, understanding this integral is very important. Here we are taking the integration of our function with our variable from 0 to infinity. So if we assume that this is our function f of t, and this is our variable t, and let's assume that this is our chart. So from 0 to infinity, so integration from 0 to infinity of our function f of t, that means the entire area under this curve. Now, at the same time, Laplace have multiplied our function with this term, e to power minus s of t. We know that a number to power of a variable is a sort of expression that the result will end up within the same domain of that function. So, as a matter of fact, in calculus, we have learned that the general formula of any function can be written as a constant multiplied by e to power another constant times t. So this is the sort of expression that the result of that will end up within the same domain of the function with that variable. So what Laplace is actually doing here, if we look at this integral, once we solve that integral for our variable t, the result will be a new function that they usually show that by the capital letter of the same, with a new variable. Once we solve this for t, we are going to have a new expression in terms of s. So we are going to have a new variable by s. So what Laplace is actually doing in here, within the same domain, he's changing our function from f of t to f of s, and our variable from t to s. So let's assume that this is the chart for the new function with new variable. And once we get this this new function with new variable, then we can use the inverse transformation steps and write the result in the form of our original function. So if Laplace transformation of f of t is equal to f of s, therefore Laplace inverse of f of s will be equal to f of t. So the step for Laplace transformation is this formula. So the only challenging part in this, is the integration formula. So it's very handy to have a math handbook that have a list of a lot of integral formulas. So this is the step for Laplace transformation that help us to transform our function and variable into a new function with a new variable. And once we get this new function with a new variable, the inverse transformation step will help us to write the result in the form of our original function. Now, once we have the new function with the new variable, the inverse transformation step. So to get the inverse transformation, the first step is step 1 is find the poles of f of s. What does the poles of f of s means? By looking at this integral, we will see that the solution to this integral will always be in the form of a numerator divided by a denominator. So it will be always in the form of a numerator divided by a denominator. So since our function, since our variable is s, so our numerator will be a function of s, and our denominator will also be a function of s. So the roots of dx, the roots of ds are called the poles of f of s. What does that mean, the roots of ds? That means we set ds equal to 0 and we solve for s. So to find the poles of f of s, we set our denominator equal to 0 and we solve for the values of s. Now at this point, we will have a couple cases. We will have two cases. Once we find our poles, our case number 1 is when our pole is a real number. When pole is real number. And our second case is when our pole is a complex number. So our second case is when pole is a complex number. By complex number, they mean a number in the form of minus a plus jb. So in the problems that we use Laplace transformation, usually we have more than one pole, and in our problem we might have a few real number poles and a few complex number poles, or a combination of both. So when the pole is the real number, under this case, when the pole is the real number, the second step, step 2, when the pole is the real number, we have to find the coefficient or the constant associated with each pole. And our function, new function, fs, will be usually in the form of that constant associated with each pole divided by s minus p plus other terms. What we mean by other terms, so if we have more pole, there will be more terms added into our function. So from this expression, we can find that constant associated with each pole will be equal to the limit as our s approaches to that pole, or s minus p fs. So from this expression, we can find the coefficient, the constant associated with each pole, and once we find that, our function f of t will be equal to that constant associated with each pole multiplied by e to power our pole times t. Again, plus other terms. If we have more terms, we will have more terms. If we have more poles, we will have more terms in our function. So this is how we find f of t, our original function, when our pole is a real number. Now, when the pole is a complex number, at that point, our denominator is going to be, it can be factor to s plus a squared plus b squared. So in that case, we can factor our ds can be factored like that. And then we have to, our second step is find ps in this relationship. S plus a squared plus b squared multiplied by fs. So when, in our case, in case 2, when the pole is a complex number in this form, we can factor our ds in this form, and then the second step, we find ps in this relationship. And once we find ps, then our function then our function f of t will be equal to the magnitude of p minus a plus jb divided by b multiplied by e to power minus at sine of bt plus the argument of p minus a plus jb. So this is how we find, and plus other terms. Plus other terms. Again, if we have more poles, there is more term. So when, in our case too, when our pole is a complex number, we find the value for PS in this relationship. Once we find that, that value, our function will be, our original function will be equal to the magnitude of P minus A plus JB divided by B, e to power minus 80 sine of BT plus argument of P minus A plus JB. So for every pole that we have to find the value for f at t, and then we just add them all together. So this was the definition of Laplace transformation and the steps for inverse Laplace transformation. And in next video, I will start with some very basic examples so we can learn the steps. See you all in next video.